Okay, so hey everybody. Today we're going to be just talking about something quick. We're going to be talking about chirality. It comes up a lot in chemistry, specifically organic chemistry. Chirality is basically from the Greek root word of hand. So when something is chiral, you can think of your two hands right here. And when I think of chirality, I think of being able to superimpose the image onto each other, meaning can you place it on top of one another. So with your hands, you cannot place your two hands on top of each other and then fit right smack dab on top. There will always be a differentiation, unless of course with your hands you flip one, right? You flip them together, and now they will fit, but now this is an achiral. This is an achiral positioning. This is not chiral atoms. Or these are not mirror images, rather. I apologize. These two things now are not mirror images because one's like this, and then one had to be flipped, okay, in order for it to be superimposed. So this would not be chiral. These would be, this is chiral because they are two mirror images. This is achiral because they are not, mirror images. Your hand, your palm of your hand would not show up as the back of your hand in the mirror, of course. Although these are now superimposable, they're achiral, okay? They're without chirality. Now, your hands both being palm up or backside are chiral in the sheer fact that now they're not superimposable. And this is a big part of chirality. And I'll get more into this. When I switch to the iPad. All right. I'll just do I don't know. We'll do a red or something. Let's do a blue. We'll do a blue instead. Okay. And let's make sure we can draw on it. Yeah, cool. Okay. Let's see what type of pen. There we go. So I just kind of explained what chiral versus achiral is. Remember, achiral is superimpose, and chiral, no superimpose. Or, to make it simpler, mirror image. Pardon. This will be mirror image. This is not mirror image. Okay? Let's take a look at our chiral objects. What makes it chiral? What makes this chiral is, first of all, these are literally hands. Chirality means hand, okay? And if you look at your hands, you cannot, if they're on the same plane, we'll say, if you both have both your palms down or both your palms facing up, both of these have our palms facing down, we'll say. The palms facing and palms down, right? Both of these palms facing down, you try to put your hands over each other, that's not going to happen. These are not going to be superimposed onto each other. They're not going to fit. They cannot be superimposed in any orientation, no matter how hard you try. It's not going to happen. Therefore, they are chiral, okay? And be wary of that. Any orientation, it won't work. So that's not happening. Achiral objects is just like it sounds without, where's my page end? Without chirality. So without hands. So this means it will be able to be superimposed. Some type of orientation. This one's simple, it's just a bottle. This type of orientation, mirror object, okay, right here in the middle. You put them together, you put this bottle on top of this bottle, it easily fits. So it will be superimposed. Okay, so that's a little bit of a simple explanation of chiral versus achiral. So we'll do a summary at the bottom, just to punch it into your heads. Chiral, hands, right? Therefore, no superimposable. And if they're not superimposable, they are true mirror images of each other, okay? Achiral, and we'll do a little a with a dash. That's a prefix. This would be something generic. We'll just keep it like a bottle. It'll be like a bottle, maybe, because I'm tired as heck. These are superimposable in a mirror. You look through a mirror, that bottle was able to fit right on top of the other one. And so these ones you can play around with, if you have to even, you can play around with to get the right orientation. To fit on top. Okay, that's what we did. We did a lot of this in organic chemistry. Just one of the many fun things we do. And so we'll be transitioning over from a nice picture to an actual compound. And we'll take a look at how this compound is chiral as opposed to achiral. So I'll pull that up in a minute. Let's see here. We'll keep our current screen. Molecules imported. Hang on. Yes, we will convert it. But let's grab it, actually, because it's too dang small. Okay, now we should be okay. Okay, so let's try this again. So we just did the hand example with the literal pictures of the hands for chirality and the pictures of the bottles for achirality. Now we're going to look at actual organic compounds and see what makes them achiral. Oh, that's too big. What makes them achiral and what makes them chiral, okay? So we'll start with achiral. Now remember, again, achiral is without chirality. So they are superimposable. So let's take a look. If we have our mirror plane here, it's already set up for us. We have our mirror plane here. Let's see what matches up. Well, these hydrogens right away, these vertical hydrogens on the, on just the XY axis, these are easily checked off. These are all good to go. This carbon in the back here, in the negative axis, you could say, right? Because we have a flat plane here coming through. you have your ones going behind, and you have the ones coming in front of you, okay? We can talk about that in a different video, but this carbon's going behind. So this carbon going behind right now, this is the same carbon, we can check this one off, as this carbon right here, to the right as this carbon, because it's also going behind. And then this little functional group of 2 carbons, or this little chain rather, will be the same as this carbon group. Let's see if I can do some of this pencil stuff. Maybe not. But this carbon here, yep, and there it is. This carbon here is the same as this carbon here, because they're both in front. Okay? So basically all we gotta look for is are all of these functional groups, or all these chains of carbons too, on the same axis. Now, what do you think helps make this achiral? How can we change this functional group on the right, okay, to match it with the functional group on the left? Because we can do it. And all we're going to actually do is flip it about 180 degrees to the left on this axis with the hydrogen. So we're basically going to have our starting point here, and we're going to turn it 180 degrees, so that now these 2 hydrogens still on that neutral plane, they're now going to be, if I can draw this here, they're now going to be on the left, okay? And then we'll have our little carbon here, and our little C group there. And it's the same thing, you got your CH2, let me just draw that in, CH2, CH3, that looks nothing like it, but you get the idea. All we did, and this is the same exact molecule, right? That's the same thing. And so now they can be superimposed. I can fit this one here right on top to this one here, okay? All I did was kind of flip its orientation. Now, I didn't flip it around the bottom. I didn't really move the carbons, because I didn't want to move the carbons. And I didn't want to move the carbons because I looked at my first molecule and I saw they're already in the right position. So I just kind of figure out, how am I going to move my hydrogens so that they look like the first compound? And I can move them by flipping this molecule 180 degrees counterclockwise. And that's what I did. And so I'm going to undo a lot of this markup here, if it'll ever go. And we'll go down to the second one. Oh wait, I want to talk about one more thing with this first one though, the achiral atom. If it will ever undo my stuff, maybe it won't, I hope this. Oh, here we go, okay. Yep, it just deleted that center. Great. I was afraid if I use my eraser, it'll actually erase the picture, and it did. So that's nice. But another thing you can look for when you're trying to figure out if it's achiral, okay? Can you move it around? You know, that's a good idea. Can I move it around and play with it? But also, there's a big hint here in the first part, in this first molecule, that will tell you it's chiral. And that is if you look at the center carbon and you look at the functional groups, we have 2 functional groups that are the exact same. That's how you can help tell if it will be chiral or achiral. If you have two or more chiral groups, at least two, because it works. If you have two or more functional groups on here that are the same, there's a strong chance that it will have the ability to be achiral, and you can superimpose them, because you can play around with these other two carbon functional groups if these hydrogens here don't have to be relevant, if that makes any sense. You can kind of just leave these two guys alone here so you can mess with these carbons and get them to fit. Okay, and it wouldn't matter if it was like an OH group and an OH group, these would still be achiral. So will it move around? And you have, we put R, the functional groups, like, are they alike? Okay, are they alike? If you have two or more functional groups that are alike, then this atom, this molecule, is probably going to be achiral. Now keep that in mind as we move down to the second chiral atom. What makes our second guy here chiral? Well, let's see. You can kind of try to play around with the carbons on the bottom here, right? And what we want to do is we're going to try to superimpose it. So we'll be like, okay, we have our carbons here at the left, and we have our compound here on the right, and we want to put it on, or put it in an orientation in such a manner that it will fit on top of our compound on the left. Can we do the same thing that we did up here and just rotate it 180 degrees? The answer is no. But why? Why is that? It's because this compound has 4 different functional groups on it. 4 dissimilar functional groups. Let's write that down. That's a good word. 4 dissimilar groups. Okay. We have a hydrogen. We have a, let's see, monoene. I always just start at propane for 3. We have a 2 carbon system here, a 1 carbon system here, and an alcohol group. I have to brush up on my carbon naming. But what this means is we're going to have a heck of a lot harder time trying to superimpose it. In fact, we can't, because we have no like groups that we can just set to the side. We have to think about all of our groups here. And so, yeah, we can keep the hydrogen and the alcohol in the neutral plane and worry about our carbons. But let's take a look at what happens when we try to move it. So I'll move it around on the right molecule here, and we'll draw it again as if we moved it. Well, let's see what happens. Let's see, let's put my pencil again. So we move it around, then I'll do this, draw that, and then we'll go back. Okay, we'll flip it 180 degrees to the left, just for shits and giggles. If we move this 180 degrees to the left, or rotate it rather, our alcohol on the right molecule is now going to be in our bottom left neutral plane, okay? So already we're seeing the similarities. Our hydrogen is going to be on the top neutral plane, okay? And then our CH3 and CH2, 2-carbon group will still be in front. So let's see, CH2 and then CH3. And then our CH3 monomer group will be in the back. So those carbons are good now. But what's wrong is our neutral plane with the hydrogen and the alcohol. Okay? So that's why this is chiral right now. This is still chiral. But now you might say, but wait, Kyle. Now, even though this is still chiral, maybe we can flip the alcohol and the hydrogen so that'll fit. Well, let's try that. Let's flip the alcohol with the hydrogen group and see what happens. So we're basically doing another 180 degree switch around this axis of rotation, around this middle axis like this. So let's see what's going to happen here. So let's draw it again, our little base platform. There's our neutral plane, what's coming towards us, what's going away from us in the negative plane. And we'll have our OH up top. Again, that looks good. Our hydrogen on the bottom. That looks good, okay. And now look at our carbons. What happened to our carbons? Well, our carbons, this is what's going to happen. We've essentially switched because we've chosen, because that OH and this CH2, CH3 have to stay on that side. We can't rotate this neutral plane without having to also rotate our positive and negative planes. So they still come into play, okay? So we've done a 180 degree flip with these. I'm gonna erase some of this because that's getting messy to me. We've flipped the neutral plane hydrogen and alcohol group, but at the same time we have also flipped our carbon chains. And so now in our left-handmost compound, while we have a good-looking OH group, we have a good-looking hydrogen group, we still have now our problem is our carbon groups are not in the same, or in the right axis, on the right plane rather, sorry. And so, long story short, like on South Park when they went ziplining, long story short, there's no real possible way we can try to superimpose this and make it fit right on top of our original atom. So this molecule is indeed chiral. And let's make this a little smaller maybe. Yeah, there we go. And so you can play around with it a lot. Usually your teacher will give you enough time and not enough problems so you can kind of try to figure it out. But something I would always look for, let's erase some of these. I'm going to erase this practice one we did here. This will we know it's chiral, it says it. And I like this example. I like this example here because it would kind of trick you if you don't know what you're doing. You can say, oh, I can just kind of try to flip the OH and the hydrogen group, and then they'll be the same. Well, no, it won't, because you gotta remember your other two functional groups will also move if you move the neutral plane, okay? So keep that in mind. But like I was saying, what was I saying? Your teacher, if you're doing like beginning organic chemistry or whatnot, should give you enough problems, and by enough, I mean they shouldn't give you a lot at all, maybe like 4 or 5. They should give you enough problems for the time frame they're doing the testing for you to kind of screw around with the molecules and try and superimpose them if that's what you so choose to do. That's what I did a lot when I was taking my time. A fast way you can determine chirality and achirality is with, let's see if I can kind of move this around. I can still write over here. Yep. So we can determine oh man, that's fat as hell. The heck? Achiral and then chiral. Okay. Chiral, remember, is hands. And then achiral, I don't know, without hands, or bottle. Twins, right? We'll do twins. I don't know. Fuck. But achiral, I would say for both of these things, move it around. Okay? Move it around. Play with the molecule a bit. Can you try to fit it into an orientation where another molecule of the same thing could fit on top of the other one? Can you superimpose it, okay? Move it around. Will it superimpose? Achiral molecules will. Chiral molecules will not. And then one more. Why does it do that? What the fuck? And then achiral molecules, this is the best tip. This is a very fast way to check if it's achiral or not. Achiral atoms or molecules will have 2 or more, so we'll say 2 plus like groups, okay? That way you can kind of forget about one of the planes or one of the orientations, like the 2 hydrogens we had over here. These are a big part of why it was achiral. So if you have 2 or more like groups, play around with it because there's a strong chance it'll be achiral. Chiral molecules, more oftentimes than not, have 4 unique, we'll say 4 unique functional groups. Okay. And that means it would be like an OH, an amine group, can do a carbon chain here. We'll do it just that's white now, nice. Let's do kind of a carbon chain here. Right, C, 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 C. Okay, carbon chain. And then what else could we do? Heck, I don't freaking know. We could do just a hydrogen. Let's just keep it simple for now, because I can't really think of anything else. But it would be 4 unique groups stemming off of the center carbon. Now, there is no way in heck you would be able to try to get this to be achiral. You can try, but you'd fail. And why? Why is because it has those 4 unique groups. So always be on the lookout for that when you're looking in the chirality versus achirality. Okay? Hands versus no hands. Do you see the 2+ groups that are alike? If you do see those 2+ groups that are alike, I'd say play around with it in your mind, or even write it out on the paper, right? And try to superimpose another molecule of it. Can you make it fit onto itself? Okay? And if you have 4 different groups that are unique, that is definitely going to be a chiral molecule. Okay? I think that's all I have for now for this episode. It's just a brief introduction on chirality. I'm not a teacher or professor by any means. This is also more for my own sanity and looking back. But if you have a question about chirality, chemistry, biology, anything pre-med related, you can go ahead and leave a comment on this video on my YouTube, or even you can go ahead and add me on Snapchat and ask one, or go to my Instagram and ask a question. And I will definitely answer Snapchat and Instagram questions more, because YouTube's comments scare me. So it'll be a while if I even comment on a YouTube or reply to a YouTube comment. So definitely hit me up on Instagram or Snapchat if you have any questions about chemistry or biology. I can answer them to the best of my ability. So thanks, guys, and you have a good night. I'm going to try to get some sleep.